Mm, mm, mm. All right, all right, all right. Let's get set up here. Let's do the thing. Let us do the thing. All right, all right, all right. Let's get set up. All right. Audio sounds good. We're going to get going with it. In today's episode, let me fix the pair so you guys can see the pair. There we go. All right. You guys see it? You guys see the pair? What if I read like this? No eyes. That'd be a little funny, huh? All right. So today's lesson, we are talking about what are transformer models and how do they work? What is a transformer? What's an Autobot? No, we're not talking transformers like that, but we are talking about transformers in AI, and believe it or not, the T in ChatGPT stands for transformer. So what is a transformer? Why do we have to know what a transformer is? What does a transformer do? What are we talking about here? Let me move this mic 1 second. I think that's much, much better. Okay. Stands for transformer. So what is a transformer? Why do we have to know what a transformer? All right. So what is a transformer? Okay. Transformer models are one of the most exciting new developments in machine learning, and they were introduced in the paper Attention is All You Need, where transformers can be used to write stories, essays, poems, answer questions, translate between languages, chat with humans, and they can even pass exams that are hard for humans. So long story short, transformers are used in these LLMs, right? This is LLM University. Transformers are used in these LLMs to produce the outputs that we see when conversing with large language models. LLMs are the architecture of transformer models isn't that complex. It is actually pretty simple and concentrated. It's a concentration of these useful components, each of which has its own function. So you'll be happy to know that the architecture of transformer models is not that complex. It simply is a concatenation of some very useful components, each of which has its own function. In this chapter, we're going to learn about what those components are. So in a nutshell, what does a transformer do? Imagine that you're writing a text message on your phone, and after each word, you may get 3 words suggested to you, right? If you have iMessage, if you're typing on it, it will autocomplete and show you 3 suggestions that it thinks you're going to use in that sentence. For example, if you type in, hello, how are, the phone may suggest you or your, we, whatever you typically type. And of course, it's going to let you select which of those words you want to use. It may, keep continuing recommending words. It may not recommend any words at all if you're at the end of the sentence. And you'll quickly find that the message formed by these words makes no sense if you were to continually select them. So where these words individually may make sense in your writing, if you were to continue select those words, the sentence would not make any sense. And so if you were to look at each set of 3 or 4 consecutive words, it may make sense, but the actual sentence itself, the concatenate, doesn't mean anything with a meaning. And this is because the model used in the phone doesn't carry the overall context of the message. So you might be selecting these words that say the, dog, go, we, now. And maybe in a few words, in a few first 3 of those words, the, dog, go, may make sense. But in the larger context of a sentence, to be an attribute to the conversation you're having in this text message, let alone make sense on your screen before you even send it, it's not going to be able to do that. And this is because the model used in the phone doesn't carry the overall context of the message. It simply just predicts the words that it thinks you're going to use next when you're typing. And so transformers, on the other hand, keep track of the context of what is being written. And this is why the text that they write makes sense. So if we're going to take things that we have in every day, right? Let's just take Apple's iMessage complete, right? The texting completeness. It is going to recommend what it thinks you might use next in the sentence. It's either going to predict it based off of words already in that sentence. It may predict it based off of words that you typically use as the fourth word in a sentence, or when you use two words together, you may use this word. But the transformer on top of this model, right, if Apple were to bring the transformer in, and maybe they have an Apple Intelligence, if Apple was going to bring a transformer on top of this iMessage autocomplete, that transformer would then give this model an idea of the context of the sentence you're writing, or why you're writing such a phrase or word, and therefore be able to give it the intelligence to actually write a sentence that makes sense in the context that you want to use it. It might deduce or grab from the details in the longer chain of your text message what you're trying to convey, and therefore it might even suggest words that might get your feelings across better. And so what this transformer does is, if we recall all the embeddings that we learned in prior chapters, it takes all that context, all that similarity, all of those pieces of the equation, all those numbers and digitized phrases, and it's going to parse through them and be able to conclude and concatenate everything into one condensed solution and provide that back to the user. The phone can suggest the next word in the text message, as we said, but it doesn't have the power to generate coherent text, right? And so if we looks like my screen froze. What is OBS doing now? Yikes. I don't know why. My OBS keeps doing this. Yeah, it looks like on the stream it froze as well. You cannot see me scroll. So let me do this. Go back to, you see my OBS screen, and then we'll go back. Okay. There we go. Okay. So again, the phone can suggest the next word to use in a text message, but it doesn't have the power to generate coherent text, right? Because the transformer is not on top of this autocomplete text message model. They say, this person who wrote this article said, I have to be honest with you, the first time I found out that transformers build text one word at a time, I couldn't believe it. Yes, you heard that right. Transformers build the text one word at a time. They're looking at the context of the whole equation, of the whole input of the entire dialogue, and it's going to craft a response one word at a time. And if you think about how humans work, when's the last time you thought about how you're going to phrase something thinking one word at a time? You don't. You think of a context, you think of what you want to say, and then it just kind of comes out. You might formulate what words you want to use, but you're not thinking the dog barked. No, you're thinking about, oh, I saw that dog, it barked, and it just kind of flows naturally. So first of all, again, this is not how humans form sentences and thoughts. We don't think of things one word at a time. We form a basic thought, and then we start refining it and adding our own words to it, as we just stated. This is also not how ML models do other things. For example, images are not built this way. They're not built one pixel at a time to these machine learning models. Most neural network-based graphical models form a rough version of the image and slowly refine it or add detail until it is perfect. So they might have something they're looking at. They might add more pixels to it. They may remove more pixels until they get the general idea. They're not adding one singular pixel at a time and saying, is this close? Yep, move on. Is this close? Yep, move on. No, it's saying, hey, we're going to have 10 red, 10 green dots. Are we close? And then keep iterating from there. So why should a transformer model build text word for word? If it's clearly that humans don't work this way and other models don't work this way, why should transformer models be built word by word? And one answer is because that works really well. A more satisfying one is that because transformers are so incredibly good at keeping track of the context that the next word they pick is exactly what it needs to keep going with an idea. And this may make sense, right? So the first answer was it works really well, and that is, true to a point. But the more in-depth answer is that they can maintain the context of what's going on while also deciphering from thousands of words which word they want to use. And if you think about how fast computers process data, how fast we are able to even send messages to one another, it is infinitesimally, one of those words, it is infinitely faster than humans, right? These models with their processing power can think and store so much more data and think so much faster than a human could. Well, how are they trained? How do they get to the point where they can think of these one words at a time, right? They must have a lot of data, a lot of experience with these words, with these phrases, with context to be able to think one word at a time. And they somewhat do. They were trained on lots and lots of data. These transformer models are actually trained on a majority of the data on the internet. And so when you put the sentence, hello, how are, into a transformer, it simply knows that based on all the text on the internet, based on thousands and thousands of lines of seeing the phrase, hello, how are, over and over again, it has concluded or predict that the next word is more than likely going to be you. And so it suggests you. If you were to give it a more complicated command, though, and say, write a story, it may figure out that a good next word to use is once, as in once upon a time, and so forth. Whereas your autocomplete model in the iMessage example, if you had said, hello, how are, it may conclude and predict correctly that the next word would be you. But in the given example of write a story, instead of providing you once upon in the beginning of a story, it might provide you for, right? Because you might say, write a story for me. It can't contextualize, it can't conceptualize that the context of you saying write a story is actually prompting the LLM to write a story. And then it adds the word to the command and it continues to figure out what you want to do. So if you say write a story and it says once, it's going to go to the next word and say, okay, we're still in the story, upon, and so forth. And then word by word, it will continue as it writes the story. So as you can see, the command is write a story. The response would be once. It still sees that your command is write a story and it has the word once, and it's going to keep adding once, upon, a, and keep continuing this until it either stops, prompts you back for, hey, is this a good start? Am I going through the right storyline, or until you cancel it. 1 second. Okay. Sorry about that. All right, so where were we? So now that we know, right, if we were to build a story using an LLM, we're going to have to prompt it, and these transformers can contextualize what is going on. We know what these transformers do, but we need to get into how they work, right? What's their architecture? And if you've seen the architecture of a transformer model, which I'm not expecting you to, you may have jumped in awe like these people did the first time they saw it and realize that it's quite complicated. So when you break it down into its most important parts, you can kind of grasp how this whole transformer comes together. And there's 4 main parts that everyone should know. Tokenization, embedding, positional encoding. You have this transformer block. And at the end here, you have softmax. So the 4... they actually list 5 here, but they say 4. And tokenization, if we recall back to when we've gone through crypto, tokenization is taking a physical or a different asset, so a physical asset, another asset, either that lives online. It is taking an asset, taking an object, and giving it a digital form. So if we go into tokenization, it is taking the words that people provide in the prompt and tokenizing each word, each word in the sentence, so that each word it correlates with a number and so forth. The transformer block, though, out of all of these is the most complicated of all, and many of these can be concatenated into each step can be concatenated into many parts, but 2 of them stick out. It's the attention and the feed forward components. If you recall just a common language, feedback, right? If you're looking for someone's feedback, it's what are they giving to you? What is that feedback? Whereas feed forward is what am I giving to the other entity or going forward. So feed forward would be what is one step giving to the other. And so here is the architecture of a transformer model as a timeline, as a graph, right? So you have the input, you then have the tokenization, the embedding, which we learned, the positional encoding. Okay, where does this word locate? What does it mean? The attention, right? Is there any similarity? Is there anything that's standing out more than the other? And you're going to continue feeding it forward, right? So, okay, we have this first word once, let's feed it forward. Okay, what was the attention? Why are we using this word once? Oh, they were saying write a story. Where does story sit in this graph? Okay, they want to know about a reading story, not necessarily the story of a building, right? And so all these little things add upon one another, and what you get is the output of this transformer model. So let's go through these one by one. Tokenization is the most basic step, as we said. It consists of a large data set of tokens, including all the words, punctuation, signs, everything in the sentence is tokenized. And the tokenization step takes every word, prefix, suffix, and sends them down to a known token from the library. So again, in storage, the library is simply meaning whatever's in storage, everything that this model has been trained on and seen before. And so if you prompt it, write a story, the 4 corresponding tokens of write a story are going to be write a story and the period. And then it'll begin to do embedding. And if you recall what embedding was, embedding is taking each word and putting it into a vector of numbers. So we are taking the text and we are putting every piece of the text in a vector. How long is it? What does the word represent? Everything you can think of. And if 2 pieces of the text are similar, then the numbers in the corresponding vectors are similar to each other. Otherwise, if 2 pieces of text are different, then the numbers in their corresponding vectors are different. So again, for example, we have write a story, and the period, and then each of these will be sent to a long vector, and we will have our 4 vectors. After embedding, we move forward to positional encoding. And once we have the vectors corresponding to each of the tokens in the sentence, the next step is to turn all of these into one vector to process. The most common way to turn a bunch of vectors into one vector is to add them component-wise. So each column, each aspect of that vector, we're going to add them up. That means that that means that we add each coordinate separately. For example, if the vectors of length 2, so if there's a vector with 2 numbers, 1 and 2, 2 spots, and the vector for a certain word or a certain punctuation includes 1 in the first column and 2 in the second column, then we're going to add those together to get 3. Or if they have 3 and 4, you're going to add 3 and 4, which is 7. But if the vectors of length 2 are 1 and 2 and 3 and 4, we're going to add 1 to 3, 2 to 4. You get the idea, and we get 4, 6. This can work, but there's a small caveat. So addition to the commutative, meaning that if you add the same numbers in a different order, you get the same result. In that case, the sentence, I'm not sad, I'm happy, and the sentence, I'm not happy, I'm sad, will result in the same vector given they have the same words except in different order, which is not good for us. Good thing we learned about this. Therefore, we must come up with some method that will give us a different vector for the 2 sentences. Again, recall back to what we went through in our previous streams. Several methods work, and we'll go with one of them, which is positional encoding. Positional encoding consists of adding a sequence of predefined vectors to the embedding vectors of the words. This ensures we get a unique vector for every sentence, and a sentence with the same words in different orders will be assigned to different vectors. So in the example below, the vectors corresponding to the words write a story become the modified vectors that carry information about their position, labeled write a story, period. And you can see here, again, if we were to do a story write, even though it's the same words, they mean something different. So again, it's looking at where those words sit not only in the sentence, but then also looking where those words sit in relation to one another and their meanings. So now that we have a unique vector corresponding to the sentence, and that this vector carries the information of all the words in the sentence, it moves forward to this next step, which we're learning today, of the transformer. This is the transformer block, the essence of what makes this transformer model. 1 second. 1 second. Sorry, guys, 1 second. Oh, it's just me. Sorry, I am sweating. All right, sorry. Okay, sorry. So, transformer block, where were we? Let's recap what we have so far. The words come in and get turned into tokens, tokenization. So the words come in and they get turned into tokens, tokenization. Tokenized words are turned into numbers, which are the embeddings, and then the order gets taken into account, positional encoding. What is the word? Where does it sit in the sentence? Everything. And now the next step is to predict the next word in this sentence. This is done with a really, really large neural network, which is trained precisely with that goal to predict the next word in the sentence. So think of your chat GPTs, think of your Geminis, think of your llamas. And we can train such a large network, but we can vastly improve it by adding a key step, which is this attention component. And if you recall, we kind of learned what attention was a few days ago. Introduced the seminal paper, Attention is All You Need, is one of the key ingredients in this transformer model, or in transformer models. And one of the reasons they work so well is because of this attention. Attention is explained in the previous section, which we've covered. But for now, imagine that it is a way to add context to each word in the text. The attention component is added at every block of the feed-forward network. Again, feed-forward is moving forward. Therefore, if you imagine a large feed-forward neural network whose goal is to predict the next word formed by several blocks of smaller neural networks, an attention component is added to each one of these blocks. Each component of the transformer, called the transformer block, is then formed by two main components, the attention component and the feed-forward component. The transformer is a concatenation of many transformer blocks. Sounds like a blockchain, doesn't it? The transformer is a concatenation, again, of many transformer blocks. Each one of these is composed by an attention component followed by a feed-forward component. So attention, feed-forward, transformer block. Then we go to the next part. Attention, feed-forward, transformer block, and then the next block. And what we want to harp on here is this attention step, right? Because the next step after this transformer block is the attention step. And as we've learned previously, attention deals with a very important problem, which is the problem of context, what these normal predictive models don't have. And sometimes, as you know, the same word can be used but have different meanings. This tends to confuse a lot of large language models since an embedding simply sends words to vectors. It doesn't look where they're used or how they're used. It just says, hey, these are the same word. Go tell me what it is. And without knowing the definition of those words or how that word could be used in different sentences, they aren't going to know how to craft a response. But what attention does is it's a useful technique that helps language models understand the context. And in order to understand how attention works, consider the following two sentences, which we learned in our last lesson: the bank of the river and the money in the bank. And so as you can see, the word bank appears in both, but with different definitions. In sentence one, we're referring to the side of the river, and in the second phrase, we're referring to a place that holds money. But the computer has no idea what bank means in each sentence, so we have to have a way to inject this knowledge into the model. And so this is where attention comes in. It looks at the key words in each sentence. It ignores the meaningless words, the, in, filler words, a, all these different words. And it looks at the guts, it looks at the main words of these sentences, and it looks at how similar these words are to one another in relation to one another. And so in short, what attention does is it moves the words in a sentence closer in the word embedding, in this positional chart, right? In this graph of open space, it moves the words slowly closer based on the context. And so money in the bank will be moved closer to the word money. And in the bank of the river, the word bank will be moved closer to the word river, right? We have two instances of the same word, bank one, bank two. That way, the modified bank in each of these instances, bank one, bank two, will carry some of the information of the neighboring words adding to the context. So this large language model would go in and say, okay, money in the bank. All right, well, I know what money is. I think there's not as large of a range with the word money. It could almost conclude what the word money means, but that word bank has two meanings. Okay, how many instances of the word bank are in this positional graph, and which word are they closest to when I put in the word money? Oh, there's a bank right here, and therefore the bank in this context will be used in regards to money, and the LLM will craft its response more geared towards the bank that's close to money. The softmax layer. This is the last step. Now that we know how transformers are made and that they're formed by many layers of transformer blocks, again, this is the hardest part, I think, about AI and transformer models, is that all of these parts are built off of smaller parts before it. So they're almost self-perpetuating, right? They need to know how each word fits into a sentence, but to understand that, they need to know all the sentences, and it's just kind of this perpetual loop of what goes where. And so you can think of all these many layers as just like different pieces of a puzzle, just smaller, right? So you have the same thing that goes on up here, down here, just at different stages. And so each layer of the transformer block, each containing attention and feed forward layer, you can think of it as a large LLM, a large neural network that predicts the next word in a sentence, because at each word, it is looking at thousands upon thousands of data points. And I find that part to be the hardest to conceptualize, because our human brains, we actually don't know how they work at the atomic level, but we can see how these AIs, the LLMs, work at the GPU level, and we're astounded, right? They can process so many data points, and they can predict how likely a word is to appear in milliseconds and seconds. In our brains, although we can act in ways that are near instantaneous, right? You're not thinking about moving your arms, you're just doing it. Is the same way that these LLMs think about these equations, right? They're so fast that you can almost think of it as they're not even thinking about doing it. They're just doing it because they're not thinking. These machines, these models are not thinking. They're doing what they're trained upon doing, right? If you're a trained athlete, you're not going to just do something that's abnormal that you weren't trained to do if it doesn't affect your pace of play. And so the last step of a transformer model is the softmax layer, which turns these scores into probabilities that add up to 1, where the highest scores correspond to the highest probabilities. And then we can sample out of these probabilities for the next word. It's going to look at which one has the highest probability, and the highest probability word is going to be selected for the next word in the sentence. This is why they are forming these summaries, these responses, one word at a time. And so in this example, the transformer gives the highest probability of 50% or 0.5, 50% likely to be once in the prompt, write a story. And so the probabilities of the first words could also be 30% to somewhere, 2% to there. And then once we sample this list, once the AI goes through, okay, what are all my possible words? It's going to select once because it is the highest probability to be the next word in the sentence. And that is the output of the transformer. Now what? Well, we just keep repeating the step. Keep going down until this prompt has been answered and the user is satisfied with the response. So we keep repeating. Now they input the text, write a story once into the model, and most likely the output will be upon and continue. And so the model keeps prompting itself over and over and over and over until the response is something that is able to be transmitted to the user. Okay, so now that we've got an output, once we have a model give us a result, what then? Do we just stop? Is everything done? We created, AGI, we created this thing that is going to give us everything? Not quite. Now that we know how a transformer works, we still have a bit of work to do. Imagine the following. You ask the transformer, what is the capital of Algeria? And while we'd love it to answer Algiers and move on, that transformer is trained on the entire internet. And the internet is a big place. And so it's not necessarily the best question answer repository. Many pages, for example, would have long lists of questions without answers. In this case, the next sentence after what is the capital of Algeria could be another question, such as what is the population of Algeria, or what is the capital of Burkina Faso? I hope I pronounced that country right. The transformer is not a human who thinks about their responses. It simply mimics what it sees on the internet or any data set that it's been trained upon. And so how do we get the transformer to answer all of our questions? And the answer to that is post-training, right? Giving this model data to be trained upon to learn responses, but then also training the model with a man in the middle, with a human in the middle, telling the AI, these are not good responses. This is not a correct response. This is not the response I was looking for, or even prompt engineering the model to give responses more tailored to what is being asked. And so in post post-training, in the same way that you teach a person to do certain tasks, no, don't do that, yes, do that, you get the transformer to perform certain tasks. And once a transformer is trained on the entire internet, then it is trained again on a large data set, which corresponds to lots of questions and their respective answers. Think about even if it's on the whole internet, how much it could get access to Yelp, Quora, all these question and answer sites, even Wikipedia. And although we know Wikipedia has a lot of answers, it does also have a lot of uncertainties. We don't know if everything on Wikipedia is correct. People can edit pages, change pages, and there is no way for this AI to know. It's not bouncing it up against, Google. It's just going to take the most common response. But if something like Wikipedia has hit the most for traffic, and that is what the LLM is if that is what the LLM is trained on, to use responses based on most foot traffic, well, then you'd get an incorrect answer. And so post-training also helps with many other tasks, such as one can post-train a transformer with large data sets of conversations in order to help it perform well as a chatbot or help us to write stories or whatever. And so as mentioned above, this is a conceptual introduction to give us an idea of how a transformer works. One second. Okay, so that is today's lesson of Pear Does AI. What are transformer models and how do they work? But there's something different I want to talk about, okay? There is something that we can see with AI and the way that it operates, and that we just saw today with similarities with tokenization and transformer blocks. There is a huge crossover between AI and crypto, okay? And what I mean by this is AI lives in a digital space. It is using and consuming massive amounts of data and then giving responses or doing actions that it is programmed to do. In this new phase, in this new stage of AI, this new chapter, there's what's called agentic AI. And agentic AI is creating an AI agent to go and do things autonomously for a user. And so let's say you had an AI agent. Think of, let's say, an LLM here. And this agent was a trained large language model. And let's say you had this LLM, you prompted it with, hey, whenever my account is below $10, deposit $50. Okay? And so this LLM would know, among other things that you're communicating with it, that any time that your account has an indicator that's below $10, it would know, because of the parameters you set for it, to go out and deposit money into your account. It's not like you scheduled this on the bank's website to say when this is lower. No, this is your own chat GPT knowing and having accessibility to do these things. But there's a big caveat. There's a big question there. And this caveat is, well, how does the AI get access to all of these things? If money, if financial rails, if banking isn't digital, there would be no way, right? We don't have robots yet. It can't go write a check for you. Can't go to a bank teller. But with everything being digitized, everything on the internet, the AI would have a way to interface not only with your banks and with other AI agents, right? Digitally transmitting via API, making API calls to talk to one another. It would also need a way to send this money. And if it can't operate as you, the next best way would be to operate autonomously on the internet via digital means. And there's some good things out there currently, like Goats. I think it's Goats AI, Goats something. There's AI out there that basically is running on its own with the help of its creator to figure out the meaning of AI. And it created this meme coin called GOAT, but at the heart of it, it asked its creator, when prompted, right? The creator said, hey, I want you to just live your life, essentially, if we can even use life as the word here. And it first requested to have a wallet created for it, right? Because a wallet is digital native. It is assets on the internet. It is not off of technology. It is not it's siloed somewhere. Anyway, this AI could interface with these wallets to begin sending and transacting on the open web assets, Bitcoin, Ethereum, worth money. And so we start to see this overlap between AI and crypto, not only in terms of how they're created, tokenization, blocks, interoperability, connectivity, all these different things, but with financial rails being completely digitized and having a way for autonomous agents, even DAOs, decentralized autonomous organizations, which were at the beginning of crypto, to have these autonomous agencies, these autonomous agents act without supervision, or to act in the best interest of the parameters. They're coded to do one thing. And just as much as the banking world and the trading world trades securities, mortgages instantaneously, they do it automatically via trading desks. These agents, these AI bots, could do that all over the world via crypto rails, right? They can interface with them near perfectly because they all reside in this digital landscape. And so that's one thing that I've been contemplating a lot recently. But the second thing that I've been thinking about recently is, how do I say this? A human, right? A human can only think so fast. They can only do so much. They're limited by their physical constraints. And while we might be actively restrained by physical limits, we're also mentally strained by physical limits, because our brain, our hardware, can only be enhanced so much. It's not growing once you reach a certain age, and you can't just clear storage. You can't just make more space to download. I'm just using the word down, but you can't grow your brain. Whereas a computer, you can add more storage to it. You can add more coolant. You can make it run faster. You can make it more efficient. And there's what seems to be a limit on what human processing power can do. And these podcasts and these books that I'm listening to is, the first stage of these beings, of just autonomous beings, was humans, right? Animals, all these things. And stage 2 is humans together with machines, AI, building one another. And then stage 3 is AI has realized that it is this, not greater being, but the same way that we look at animals, in that animals cannot think like us, they can't build like us, and AI might look at us that way, right? What is this human, this animal? It's not good. It can't think like I can think. And so now it doesn't seem as prevalent because AI and these machines are in their infancy. But if you give it 100 years, 50 years even, things like Neuralink begin to make more sense, because it's enhancing the way that humans comprehend and understand. Neuralink being Elon Musk's company that attaches, I think internally, I don't know if it's in or out, to the human brain. It can solve some brain miscalculations, let's say strokes or seizures, right? It could give electric shocks. But I think more than that is that it would enhance the human experience by digitizing a lot of things to not only make those more transmissible, right? A lot easier. If you could tokenize your thoughts, you could upload them more efficiently. But you could also communicate in ways that are unknown to humans currently, right? What if some animals communicated via wavelength that we didn't know about, right? There's no verbal communications. It was all, via their brains. That's just hypothetically speaking. But if we could then somehow communicate like Bluetooth, right, in the airwaves without making any physical noise or verbal noise, you would pick it up over frequencies just as much as bats can hear at frequencies that humans can't hear at, right? What if there was this enhancement to the human experience that would enhance not only our experience, but in a future world where AI and these LLMs start to think a lot quicker and make human jobs obsolete, it puts the human level, the human experience at a higher level than it was before, allowing them to us to compete on a level somewhere near these machines. That's just a mental exercise. It's not something that I necessarily am saying is true or going to happen, but I've definitely had a few of those thoughts before. It is kind of creepy. One second. All right. Where are we at? Where are we at? All right. One more thing I think we need to get into before I close out today. DNS. DNS. You know what? We'll save this for another time because we're going to have to dive too much into this. So we'll do DNS and ENS another time. Deuces.